Hello dear student, today the topic of my lecture is derivation of Sabine's formula for reverberation time. Sabine's formula is a very important topic in the field of architectural acoustics. Architectural acoustics is basically a part of physics which deals with the control of the quality of sound inside different types of building like halls or say auditorium, say conference rooms, etc. So since the purpose of this control is to create a condition by which people can hear with comfort, it is very much necessary to consider not only the principles of sound but also to take into account the quality of sound. Now whenever we think about this hall, auditorium and conference room, you might be thinking that there are difference of size to this particular rooms. If you consider auditorium, if you consider conference room, in all the cases the requirement of the sound will be different, the audience will be different. So architectural acoustic is that part of science which takes care of the quality of sound. It should be with a good loudness, and it should be with a good clarity. So for that, for making a good auditorium or for making a good hall or a conference room, for building this particular structures, we need to go to the basics of the sound phenomenon related to sound that happens inside a hall or auditorium or a conference room. So all of us know that whenever we are inside this kind of halls, auditoriums or conference room, we have a speaker, okay, and we have audience. And whenever we talk about halls, auditoriums and conference room, we are basically inside an enclosure. The enclosure size may vary, and in addition to that we have different kind of objects inside the hall. It may be first we can consider the walls, then we have the floor, then we have the ceiling, and then we have furnitures, etc. So whenever the speaker speaks something, now there are so many possibilities. One is that the sound will reach the audience directly. That is very good. Another possibility is that instead of traveling towards the audience directly, the sound may fall on the surrounding walls, because sound will be emitted in all possible directions. It is not supposed to go towards the audience directly. So when the sound is falling on the other sides of the walls and furniture, some of them will get reflected from the furniture, because we know that just like light, sound also follows the laws of reflection. Fine. So when sound wave falls on the walls, some of it will be reflected back towards the audience. Similarly, some of the sound wave which falls on the furnitures will be reflected back towards the audience. Okay, so that means what will be the ultimate result of this particular thing, that we are having multiple reflection. We are having multiple reflection of sound wave. How is it possible? Because some of the sound wave which is falling on this side may go there, and then it may reach audience finally. So before reaching the audience, the sound may suffer n number of reflections. There may be thousands of reflection per second. So as a result, what happens because of that? So when the speaker says something, say t equal to 0, and say this sound should have gone, that particular tone, whatever tone is created by the speaker, should have been gone by the time it becomes t equal to 1 second. But because of the multiple reflection of the sound wave, the sound doesn't exactly goes away. Okay, so the sound still remains inside the hall or the room or the conference hall even after the source has been cut off. This particular phenomenon is basically known as the reverberation of sound. So, reverberation is nothing but the general dying out of sound with multiple reflection after the source has been cut off. So, sound reverberation of sound means the prolonged reflection of sounds from different walls, floors, ceiling of a room. It is also defined as a persistence of audible sound after the source has stopped emitting the sound. And the duration for which the sound persists inside the hall even after the source is cut off is known as reverberation time. So we have, if I want to define what is reverberation, reverberation is nothing but dying out of sound with multiple reflection after the source of sound is cut off. Why I am saying dying out? Because we know that these walls have some kind of absorption capacity. Okay, so when the sound falls on this particular wall, as per its absorption capacity, it will absorb some amount, and whatever sound is reflected back, that will be having lower amount of energy. So with every successive reflection, the amount of energy carried by the sound wave or the strength of the sound wave will be decreasing. That is why it is called dying out of the sound, or you can say the decreasing intensity of the sound wave with multiple reflection. And the time for which the sound remains inside the hall even after the source of sound is cut off is called reverberation time. So if we need to give a very standard value for reverberation time, so that is called this is called standard time of reverberation. So standard type of reverberation basically is equivalent to the time required in seconds for a sound wave to diminish from its initial intensity to 1 millionth times its initial intensity. So that means suppose the initial intensity is I, how much time does it take in seconds? Time in seconds does the sound wave takes to get down to 1 millionth times the initial intensity. So this particular time is called standard time of reverberation. So if we need to give a mathematical idea for standard time of reverberation, then we should go to this, that the time during which the intensity will go down to 10 to the minus 6 times the initial intensity. Now there is another case called optimum reverberation. So for a good acoustical hall, that means a hall or auditorium which you will call it to be very acoustically good, the reverberation time should neither be too small or too long. If the reverberation time is too long, means the sound persists inside the hall for a very long time even after the source is cut off. And if reverberation is too small, means sound doesn't properly persist inside the hall after the source is cut off. So in both the cases we have disadvantage. What happens if the reverberation is too long, if reverberation time, say capital T, is too high, then what will happen? It will create overlapping between the syllables, sound syllables. At the same time, if then the loudness will be zero, the clarity will be gone, loudness will be approximately zero. Okay, both the cases are not suitable, neither too high nor too low. So for every so if it is said this particular kind of room, a room where the reverberation time is too low, that kind of room is called dead room. So that is not at all good. Similarly, the rooms where the reverberation time is too high is called live room. That kind of room is also not good. Okay, so that means to have a acoustically good auditorium or a conference room, the reverberation time should neither be too high nor be too low. Okay, so we should find a balance between these two things where we can have a very good loudness, and also we should have a good clarity sound. So the value or the reverberation time value at which we can maintain both this thing is called optimum reverberation. Now, as we are talking about the derivation of Sabine's formula, as we know that Sabine's formula is a formula for measuring the reverberation time. Now, reverberation time is so important because if reverberation time is too high, then we have this overlapping thing, we don't have the clarity of sound, and the reverberation is too low, then we don't get the sound properly, loudness is zero. That means reverberation time plays a very crucial role in making the room acoustically good or making the hall acoustically good. That means we need to take care of this factor called reverberation time, and it is seen that reverberation time depends on the size of the halls or the auditorium, and it also depends on the quality of the materials inside the hall. So how is it related? Suppose if you have a room where absorption coefficient is high. Absorption coefficient means absorption coefficient of a material is nothing but energy absorbed per unit area divided by energy incident per unit area of that surface. Okay, so suppose that the absorption is very high, then what will happen? Whenever a speaker is emitting some sound, it will be absorbed quickly, and we have the audience here. We have the audience, here we have the speaker. So if absorption is high, the sound will be absorbed very quickly and the sound will die very quickly. It will not have that much of multiple reflection. So sound will die very quickly. So reverberation time will be very small. So it will turn into a dead room. On the other hand, if you have a room where absorption coefficient is low, Suppose we have the speaker here and we have the audience here. So when sound is emitted, absorption coefficient is low, means it will absorb low. Less amount of energy will be absorbed. So more energy will pass and it will suffer so many reflection before reaching the audience. So that means the reverberation time will be high, or not high, I should say reverberation time will be longer. So this kind of rooms are called live room. So that means how much will be the reverberation time? That depends upon the absorption coefficient. And absorption coefficient depends on the material quality. Material quality means, suppose if you have a wooden thing, cloth thing, or concrete material, all of them will have different absorption qualities. So that means now we have got an idea that reverberation time is why reverberation time is important, and on what two basic things it will depend. One is called size of the thing that you size of the hall or auditorium, whatever you are taking, and also quality of material. That means indirectly it is depending on the absorption coefficient. Okay, so that means now we will try to connect these two things, and this formula that connects them is called Sabine's formula. Now let us go to the derivation of Sabine's formula. Now for deriving Sabine's formula, we will have to make some consideration. The first consideration that we will be making is that the sound energy is distributed within the room uniformly in all the direction. So first consideration. Number one, so we will consider that the sound energy is emitted uniformly in all directions. Inside the hall or auditorium under consideration. Second consideration that we'll be making is that, so we will have to consider that at steady state, or you can say that equilibrium state, the rate at which the energy is produced by the source is equal to the rate at which the energy is increased in the medium, and the total rate at which energy is absorbed by the walls and surroundings inside the hall or auditorium. That means, again let us go through it. It says that at steady state, the rate at which the energy is produced by the source, means the power of the source, is equal to the rate at which the energy is increased in the medium and the total rate at which energy is absorbed by the walls and surrounding inside the hall or the auditorium. Now this derivation is to be done in several parts. So let us go into the part 1. Okay. So in this particular thing, we will have to consider the reception of sound energy by a small element ds on a plane wall AB. So let us consider just a wall like this. Okay, so this is a wall, say AB, and just consider the center of this wall, and we are considering a element called, say, ds. This element is ds, and now we will be drawing one perpendicular. So I will call it as a normal. Now from the center of ds, from the center of ds, let us draw two circles like this. So I will try to draw two circles. My diagram may not be that perfect, so I am drawing two circles like this. What is the specialty of the circles? They have center at the center of ds, means here. We have the center here. Now, what I will be considering, say this one, I will name it as R, and this is, say, so this is R plus dr. So this much is called dr. Now I will be considering two faces here. So this is called theta and this is d theta. So again this much is dr. Now let us consider this shaded region. Now let us consider this shaded region, that means the area between the circles. of radius r and r plus dr, sorry, r plus dr, and also between the angles theta and theta plus d theta, because this whole angle is called theta plus d theta. Now if I consider this portion, if I consider the concept of arc length, since this is r and this is d theta, so this is called r d theta. This portion will be called r d theta, and this radial length is dr. So if I ask you what is the area of this shaded portion, so this shaded area is r d theta into dr. Now for proceeding further, let us consider this portion. Now we know that this part is r, so this part will be called sin theta. So if the next question is, now if the whole figure, now we want to rotate this whole figure above the normal, this is the normal, we want to rotate this whole figure in this direction, and this time we will rotate it through an angle d phi. Now after that, what will be the situation I would like to tell you. So let me remove some of the unwanted parts. Now when we rotate this whole figure through the normal, for that I will like to draw another figure. Now this is our r sin theta, this is r d theta, this is dr, and this is the normal, and we are rotating with the whole figure around this normal in this direction. So next portion will be something like this. This will be the new position of r sin theta, and we have rotated this whole thing through an angle d phi. Now if I ask you that what is the distance traveled by this particular area, this shaded area has traveled this much distance. So distance traveled by the shaded area is equal to, again here this is the d phi. Arc length concept if we apply, this is the radius is r sine theta and angle is d phi. If I apply the concept of arc length, the distance travelled by the shaded area is r sine theta d phi. That is nothing but circumferential distance. Now if I ask you that what is a volume, now if I ask what is a volume traced out by the shaded area while rotating through an angle d phi about the normal will be, when we talk about volume will be length into breadth into height. Now for this particular shaded area, we already have the area. What was the area that we have already done? That is called r d theta dr d phi, and the circumferential distance that has travelled is, the circumferential distance it has travelled is r sine theta d phi. So volume can also be written as area into the circumferential distance. Now area is r d theta dr, and what is the circumferential distance? R sine theta d phi. So finally we can write it as r square sine theta d theta d phi dr. So this is a volume traced out. Volume traced out by the shaded area. Now let us consider that E is the sound energy density, that means energy per unit volume inside the hall or auditorium. Then energy contained inside the volume traced out by the shaded area is E into r square sine theta d theta d phi dr. But this sound energy is inside this. Let me draw the diagram again. Let me go back to the diagram again. So that means the sound energy is emitted by this area, the sound energy is inside this area. What is the sound energy inside the area? E r square sine theta d theta d phi dr. And this sound energy is emitted in all the directions. The sound energy is emitted in all the directions. But we are mostly worried about the sound received by this element ds here, that we considered very initially. This element ds, we want to know how much is energy received by the small element ds, and small element ds, it is a part of a big wall called AB, as we initially started with. So this is the energy emitted, in all the directions, total energy. Now we want what is the total amount of energy per solid angle. So therefore, energy emitted per unit solid angle along any direction, because already we have considered that sound energy is emitted in all possible direction uniformly. So we can consider what is the amount of energy emitted per solid angle. For uniform spherical distribution, total solid angle is equal to 4 pi. So per solid angle will be equal to E r square sine theta d phi d theta dr by 4 pi. Because total, if it is emitted in all the direction, that means total solid angle is 4 pi. So this much of energy is emitted in an angle 4 pi. So for one angle, one solid angle, the energy emitted will be E r square sine theta d phi dr by 4 pi. But we need to know now how much energy is received by ds. To know about ds, we need to know how much is a solid angle made by ds with this particular volume. Now for that, we need to draw this diagram. And when we consider about solid angle, whenever we talk about solid angle, we have two cases. One case is basically like this: when the area is perpendicular to you. So I will not go much into details about the solid angle. So if I want to know about this shaded area, so the solid angle is basically denoted by omega. Then it will be, if this is solid angle omega, if this is the area ds, then it will be simply ds by r square, because this thing is perpendicular. But if it is not perpendicular exactly, if it is inclined like this, the same area ds. Now this solid angle, this is the solid angle. In this case, solid angle is, instead of ds, we write it as ds cos theta by r square, where this is the perpendicular. So in our case, with respect to this shaded area, ds is in an inclined position, and what is an angle called theta. So for us, therefore, solid angle subtended by ds, you can refer to the diagram again, element Therefore, the energy in the volume element is traveling E r square sin theta dr by 4 pi. So this is the volume element, energy emitted per solid angle. But ds has a solid angle of ds cos theta. So ultimately, so here what will happen? R square cancel. So finally we have E ds dr cos theta sin theta d theta d phi by 4 pi. E ds dr sin theta cos theta d theta d phi by 4 pi. So let it be our equation number 1. So this is the energy received by ds. Now, in order to find out the value of energy reaching ds per unit time, equation 1 is to be integrated from r equal to 0 to r equal to c, where c is the velocity of light. So let us go back to this equation. So this is the energy received by ds, okay, but if we want to get how much is the energy received by ds per unit time, when we talk about per unit time, so when we integrate dr is nothing but integration of distance, okay. Now distance traveled in unit time is nothing but distance travel per unit time is nothing but velocity. And since, so instead of, sorry, I made a mistake. So it is not light, it is the velocity of sound, okay. So here when we will be considering what is the distance, what is the energy received by ds per unit time, we will have to integrate this whole thing for with respect to r, where r is the distance and distance per unit time is nothing but velocity. So instead of putting r, we can put c. So that means energy received by ds per unit time is E ds by 4 pi is fine. I will say the total energy. So ADS is fine. Now we have dr. Okay, so integration, then we have sin theta, cos theta, d theta. Then also we have d phi. We need to integrate all. So when we talk about dr, so dr will go from r to 0 to r to c. Now when we talk about theta, let us go back to the diagram. What was theta? So you can see this is your theta. So if you look at symmetry, this side angle goes from 0 to 90 degree, and the same applies to this side also. So theta will go from 0 to pi by 2. Similarly, when we talk about phi, so phi is the total angle through which it has been rotated. So if you talk about the total angle, it will be definitely will be equal to 360 degree. So when we put the limits, it will be 0 to pi by 2, it will be 0 to 2 pi, full circle rotation. So finally we will have E ds by 4 pi. Let us do one by one. Say let it be like this: 0 to pi by 2 sin theta cos theta d theta. This is d phi means 0 to 2 pi. So E ds by 4 pi, 0 to c dr, 0 to pi by 2 sin theta cos theta d theta. This is 2 pi. Yes, so pi and pi gets cancelled, 2 and 2 gets cancelled. So it is E ds by 2. Again it is 0 to c dr, 0 to pi by 2 sin theta cos theta d theta. Implies, so it is how much it was? EDS. So I can go little up. So it will be E ds by 2. So let me go to theta then. So if I multiply 2 sin theta cos theta d theta, so here again I have a 2. So E ds by 4, 0 to c dr, so 0 to pi by 2, it is sin 2 theta d theta. And we know that sin 0 to pi by 2 sin 2 theta d theta is nothing but 1. That I am not going to do derive in detail. This you can check in any 12 standard or say 10 standard trigonometry books. You can verify it or you can do on your own. And 0 to dr, so this is nothing but 1. So E ds by 4. So this is nothing but integration dr means r, so it goes from 0 to c. So E ds by 4. So that is nothing but c. So amount of energy received, total energy received by ds per unit time is equal to E ds into c. There is a very important relation. Now let us assume that A is the absorption coefficient of the wall AB so as for ds. Absorption coefficient means the ratio of amount of, it is a percentage of energy absorbed by the wall. Whenever some energy is falling on it, how much percent is absorbed by the absorption by that wall is given by the value A. So say if I say A is equal to 0.4, it means actually 40%. So that means that if 100 is falling on that wall, it will absorb 40% and it will let 60 go. Okay, so there's a kind of idea you can get out of it. So therefore amount of energy absorbed by ds per unit time is equal to, so incident falling on it is energy, amount of energy falling on it is E dsc by 4. So how much it is absorbed is A into E dsc by 4. So you can make it look much better. It is called E A dsc by 4. Therefore, but we are talking only about the small area ds. So if I ask how much is the energy absorbed by the whole wall, so total amount of energy absorbed by the complete, or I can say whole wall, by the whole wall AB is summation EA dsc by 4 is equal to E summation A into dsc by 4, or it is called E A C by 4, where summation A into ds equal to A is called the total absorption by all the surfaces inside the hall or auditorium. All the surfaces, when we say, it basically says roof, ceiling, side walls, furnitures, audiences and everything. Now let us move to the part 2 of this derivation. Now let us consider that P is the power output. So that means the rate at which energy is emitted by the source. That means rate at which sound energy is emitted by the source. If E is the energy density and V is the, I will say, sound energy, V is the volume of the hall at any instant of time, then total energy inside the hall is E into V. Therefore, rate of growth of energy is equal to ddt of E into V. Now E is the energy density and V is the volume. V will always remain constant. Energy density inside the hall will vary with respect to time. So V we can take out of the differentiation, d into dt. But as we have already discussed, at any instant, rate of growth of energy at any instant rate of growth of energy inside the hall will be equal to rate at which energy is produced minus rate of absorption. It's very simple principle. So rate of growth of energy already we got, it is d v into d dt. Rate of at which energy is produced, that we have already discussed. The rate at which energy is produced is nothing but P. So that is equal to P. And rate of absorption. So rate of absorption. So this is the rate of absorption. The program is absorbed by the whole wall, or you can say by the whole room. So it's nothing but E AC by 4. So that is E AC by 4. And it is a very important relation. So I can call it equation number 2. Now the steady state. Now at steady state, steady state means energy will not change. Energy will be constant. Energy density will be constant. So variation of energy density will be 0. So it is d dt equal to 0. So at steady state, we will consider energy has reached its maximum. So E equal to Em. So d dt equal to 0. So equation 2 implies 0 equal to P minus Em AC by 4. So which implies Em equal to 4P by AC. So this is another important relation. Let it be equation number 3. Again, let us go back to equation number 2. So equation number 2 implies V into d dt is equal to P minus EAC by 4. EAC by 4. So we will do dE dt. We will divide both sides by V. So it will be P by V and EAC by 4V. So finally we have d by dt equal to P by V minus AC by 4V. AC by 4V into E. Now I will call AC by 4Vs alpha. Say. So from this I can write 1 by V is equal to 4 alpha by AC. So from this I can write d by dt 4 alpha by AC into P minus alpha into E, because this is nothing but 1 by V. Similarly, so we have d by dt plus alpha into E and 4 alpha by AC into P. So I will rather modify it like this. So 4P by AC into alpha. I will multiply both sides. D by dt plus alpha into E by e to power alpha t. 4P by AC alpha e to power alpha t. Then I will put it inside e to power alpha t plus alpha e to power alpha t 4P by AC alpha e to power alpha t. So if I consider this whole thing, I can write as d dt of e into e to power alpha t. So you can consider e is taken as constant. d dt of e to power alpha t will give alpha into e to power alpha t. Again, if you consider alpha t as a constant, alpha t will come here and then you will get d by dt like this. So we can write it like this. So it goes to 4P by AC alpha into alpha t. So now d of e to power alpha t 4P by AC alpha e to power alpha t dt. So if I integrate both sides, e to power alpha t 4P by AC alpha e to power alpha t dt, and there will be a constant. So it will be e to power alpha t. Then we will have 4P by AC alpha e to power alpha t by alpha, because integration e to power alpha t dt is nothing but e to power alpha t by alpha. Alpha gets cancelled, constant. So finally it looks like e to power alpha t 4P by AC e to power alpha t plus constant. It will be our equation number 4. Where k is a constant of integration, which can be determined by using boundary conditions. Now let us consider the case 1. Growth of energy density. So consider that you have just started the source. So at t equal to 0. At t equal to 0, you have just started the source, so E also is equal to 0. Therefore, let us apply this equation. Therefore, equation 4 implies, what is the equation 4? E into e to power alpha t 4p by AC 4p by AC e to power alpha t plus k. So, apply this condition. 0 4p by AC into 1 plus k. So, k is equal to minus 4p by AC. Therefore, question 4 implies E into e to power alpha t 4p by AC e to power alpha t. In place of k, I will write 4p by AC. So, 4p by AC common. E to power alpha t minus 1 into power alpha t. So, E is equal, dividing both sides by e to power alpha t, we will have 4p by AC 1 minus e to power minus alpha t. Dividing both sides by e to power alpha t. And 4p by AC. If you look back, 4p by AC is nothing but EM, equation 3. So, 4p by AC is nothing but EM. So, we have EM into 1 minus e to power minus alpha t. So, this is the pattern in which the energy will grow. So, if you look at the plot, it will go like this. So, this is E and this is T and this is somewhere EM. This is the growth curve of energy density. Now, checking the